Okay, welcome everybody to another Origin seminar. Today we have a talk from Mathew Murphy, who's a graduate student here at Steward Observatory, and he's going to talk about WASP-43b and probably a hot Jupiter.
Yes, thank you. It's good to see everybody, and I hope the audio is coming through well on Zoom. I presume someone will yell at us if not. Over the next 40 minutes or so, I want to teach you all about weather on exoplanets and really how both an appreciation for weather and understanding how it affects our observations are both very crucial to making sure that we're really getting accurate insights into what these planets are really like. And I want to start off with a bit of a story about something that taught me why weather is something that's important to consider. My path into studying exoplanets really began with a fascination for the planets within our own solar system. And as with many other people, really fixated on Mars. And as we speak, the Perseverance rover is patrolling Jezero Crater, serving as what's really NASA's first astrobiology mission. And so far, it seems to be the case that Mars is likely a dead planet right now. But this wasn't always the most prevalent idea. And in fact, less than a century ago, analyses of Martian life were appearing throughout the literature. And even up the road at Lowell Observatory, observers were taking photographs of this Martian vegetation and even trying to take spectra of it. So what happened? This image is a reproduction of a photograph of Mars taken at Lowell Observatory in 1924. And all you should really see here are some patchy dark spots and some bright spots on the planet. More photographs were taken up through 1926. And the dates here roughly represent like the equivalent Earth season that it would have been on Mars at that time. What struck a lot of people about these photographs is that as you look at them through time, these patchy dark regions seem to be growing, receding, and altogether changing in shape. These waves of these dark regions were thought to be these vast patches of vegetation that would grow and recede with the changing Martian season. But what we came to realize, however, was that these weren't actually cascades of life, but in fact, we were witnessing storms. These two images are more recent images of Mars taken from Hubble. This image on the left shows a pretty clear day, pretty cloud-free day on Mars, where you can see all the way down to the surface, which is characterized by these dark regions, these light regions, which are just two different surface types. This image on the right was taken only a few months later, where we can no longer see all the way down to the surface, but instead it's been covered by this thick layer of dust. Martian weather is really driven by these global dust storms, which periodically obscure, reveal, and shroud portions of the surface, which in these early observations mimic the coming and going of life. So as we continue into this new era of exoplanet research, it's important to keep this lesson in mind of how these weather phenomenon and really a lack of understanding of them can lead to wild misinterpretations of what's really happening on the planet. So now that we know that weather is something worth thinking about, how do we actually treat weather on an exoplanet? And in fact, this is a very complicated problem. Early on, exoplanet observations were interpreted using one-dimensional cloud-free models, where the entire atmosphere would be treated as a single vertical column, allowing the temperature to only vary in the vertical direction, which is the pressure dimension. And this figure on the left here shows an example of this 1D temperature pressure profile. And this would be applied to the entire globe, like averaged out into one column. Then given some observation, like a transmission spectrum, for example, we would try to fit this 1D temperature structure, take some specified set of molecules, and fit their mixing ratios as a function of pressure, along with this thermal structure, in order to match that observed spectrum. And this approach did a pretty good job at getting an idea of the composition of these atmospheres. but it really couldn't capture any weather phenomenon, particularly because it's 1D and averages over the entire planet, whereas weather is really a global 3D effect. And even beyond just thinking about weather, planets are inherently 3D. And treating this three-dimensional domain is especially important for planets like hot Jupiters, which, since they're tidally locked, have huge differences in the radiation environment experienced by their day sides versus their night sides. So with this in mind, three-dimensional models began to develop, which split the globe up into some set latitudinal, longitudinal resolution, and would assign independent temperature pressure profiles to different points around that globe. This way we could track how the thermal structure changes, not only vertically throughout the atmosphere, but around the entire globe. This figure here shows an example of this from a 2008 work led by Emily Raucher. And this just shows the disk projection of a 3D temperature map of a hot Jupiter as a function of its rotational phase, where your brighter is hotter and cooler colors are cooler. And I'll just briefly step through this figure to make sure it's clear. At the left, at a phase of -1/2, we're looking at just the day side of the planet, which is very hot. And going left to right, we see it rotating so that the day side is rotating out of view as if like the right edge of the disk was rotating out of the plane. And then so going left to right towards a phase of 0, we're now looking at the cool night side. And then continuing on, the day side rotates back into view and we see it's hot again. These models were excellent for giving us insight into the global temperature structure of the planet. But since they didn't include clouds, we still couldn't get any insight into this idea of cloud-driven weather. Many state-of-the-art atmosphere models, which do include clouds, use what's called this post-processing method, where here post-processing just means that the clouds are added in at the end. And the way that these models work really is you take a high-res, three-dimensional, cloud-free model, run that forward to map out the temperature structure of the planet. And then once that reaches some sort of equilibrium state, we stop it and then add in where clouds would be expected to form, given that final temperature structure. These figures are basically an example of this from a fantastic work led by Christian Helling last year. Both of these plots show an equatorial slice of the planet, as if you were looking top down and just took a cross section of the equator. And so these just show how things vary as a function of pressure and as a function of longitude around the planet. And in these, the left-hand hemisphere is the night side of the planet, and the right side hemisphere is the day side of the planet. This figure on the left shows the thermostructure of the planet from this initial cloud-free model, which they took and computed where clouds were to be expected to form given that, which brings us to this figure on the right, which shows, or which plots the cloud seed formation rate. With these post-process cloud models, the clouds aren't actively evolving along with the thermal structure of the planet. And so we can't really run them forward in time to see how cloud patterns might evolve and how they might induce feedback on the thermal structure of the atmosphere. So while they do include clouds, they aren't really able to tackle any time variability. And in fact, modeling any time evolution of an atmosphere is a very computationally difficult problem. And few studies have really looked into that in detail.
Can I ask something? So in your previous plot, or in the previous graph, the direction from the star, from the host star, is always illuminating from the right side?
Yeah.
So there's no like orbital rotation or...
Yeah, well, it's rotating around the star or orbiting around the star at the same speed it's rotating around.
Okay, so it's guided looked.
Yeah, so the star is always coming in from this right, the direct right side. So one modeling work that did look into time evolution was this 2008 Rausch-Hurdle study I mentioned a few slides ago. This work came out right around the time that the very first Spitzer phase curves were being taken and analyzed. And they took their cloud-free model, but they allowed this 3D cloud-free model to evolve forward in time. And they recorded how the thermal properties of the atmosphere changed on an orbit-to-orbit basis. And what they found is that even when you don't have clouds, weather, which in this case would be dynamically driven, can have a huge impact on the phase curve that you observe at any particular time, specifically by changing its shape in time. They model these in each of the Spitzer band passes, and I'll just draw your attention to this bluish yellow curve, which is the 4.5 micron channel. Following this left to right in the figure, we're watching about 9 consecutive orbits of the planet. And what you can see is that as you go orbit to orbit, the particular phase or particular shape of the phase curve, especially its amplitude around the peak, is changing dramatically. So again, even though the simulation was cloud-free and the variations here are being driven just by thermal things and dynamics, the main point is that by observing the phase curve repeatedly over time, we can get an insight into how weather is impacting the atmosphere. Just to make sure we're all on equal footing here, I'll just briefly step through what a phase curve is. A phase curve measures the emission from the planet as a function of its orbital phase, which in the case of a tidally locked planet is the same as its rotational phase. So starting with this leftmost arrow, we're seeing the planet just leaving secondary eclipse. And we're looking at its hot, bright day side, which is producing the bulk of its emission. Continuing forward in the orbit, going around, that day side is rotating slowly out of view. And we're losing that emission. And this phase curve is slowly dropping until it reaches a minimum around transit, when only the night side of the planet is in view, which is cool, probably pretty cloudy, so it's not producing anything anymore. And then continuing on. Continuing on in the orbit, that day side rotates back into view. We're picking up that emission again, and the phase curve once again begins to rise. These phase curves probe the entire orbit of the planet. And so they're a great way to view the entire planet. But just as few modeling works have really looked into this question of time evolution of an atmosphere, there's been few observational studies that have also tackled this and looked at doing repeat observations to probe weather. So there have been some great works. One particularly notable one, led by David Armstrong, used Kepler to look at repeated optical phase curves of the giant planet at P7b. And what they did find strong variations in that phase curve between their observations. These 4 panels here show 4 of their phase curves. And you can see very clearly the shape of this curve between the panels is changing dramatically. And this dip in the middle here is just the planet going into secondary eclipse. At optical wavelengths, though, it's very hard to distinguish this planetary variability from any stellar variability. And this becomes an easier thing to do at longer wavelengths, particularly the infrared. In the infrared, however, the only variability survey that has been done has only used repeated eclipse observations. The team led by Brian Kilpatrick used Spitzer to look at many secondary eclipses of 2 giant planets, HD 209-458b and HD 189-733b. So look for variations in their eclipse depth as a function of time. This figure here just shows an example of that for the first planet, 209-458, showing how its measured eclipse depth, as a function of the observing date. And what they found generally was there was no variation. And when you consider the uncertainties here, the eclipse depths remained pretty constant in time. And so while this result is pretty great evidence that there isn't much variability going on the day sides of these planets, these eclipse observations only probe the day sides of these planets. And as I mentioned before, weather is inherently a global process that's acting on the entire planet. So we really do need these full phase curves and that ability to probe the entire atmosphere of the planet to really nail down the nature of weather that might be happening. But despite this, no planet has ever received repeated Spitzer phase curves in the same wavelength band. These single Spitzer phase curves that have been observed can't show signs of weather because the effects of weather would only come through in repeated observations. And as we just went through, many of the models that we use aren't really built to capture time variability, especially when including flights. So we don't really know if we're seeing these atmospheres in some state of equilibrium, or if we're instead seeing just a single snapshot of something that is changing dramatically in time between the times we observe it. And this is a very important problem. The atmospheric properties that we derive from these single phase curves, we inherently assume to not be time varying. But if weather is significant and the atmosphere is in fact changing in time, then this assumption is off. These properties may be changing dramatically, and we're really missing this key piece of understanding of how these atmospheres work. So we set out to test this, looking at the hot Jupiter WASP-43b. WASP-43b is not terribly unlike the gas giants in our solar system in terms of sheer size. It's a little bit smaller than Jupiter at 0.93 Jupiter radii. It's a little less than double the mass of Jupiter at 1.78 Jupiter masses. But where it does differ is in its radiation environment. It is a hot Jupiter, meaning it resides on an extremely short period orbit of 19.4 hours. This short orbit subjects it to very strong radiative forcing, giving it a day-side brightness temperature of around 1500 Kelvin. Now, compared to other hot Jupiters, WASP-43b receives relatively low irradiation compared to the population and is a pretty fast rotator. And this actually makes it a favorable candidate for seeing weather. That work I mentioned previously by Rausch et al., which just looked at dynamically driven weather, found that in their models, when they increased the rotation rate of the planet and decreased the radiative forcing being received by the planet, this boosted up the degrees of variation they were seeing in their phase curves. And also another bonus is that WASP-43b has already had a phase curve measure, which I'll introduce in just a couple of slides. Another thing that makes WASP-43b a nice target is that we expect it to be fully enshrouded in clouds, which is very important in this idea of having cloud-driven weather. This figure, also taken from that Helling et al. Work I mentioned earlier, shows results from a post-processed cloud model of WASP-43b. And here we're looking at a plot of the cloud particle to gas mass ratio as a function of longitude and pressure. Where again, the right hemisphere is the day side, and the left-hand hemisphere is the night side of the planet. And we see here that the night side is expected to have this thick, extensive cloud deck. And in fact, the day side isn't cloud-free either, but has a relatively thinner cloud deck. So as I just mentioned, WASP-43b had already had one phase curve measured back in 2014 from the observing program led by Kevin Stevenson. And then my advisor, Thomas Beatty, led an observing program in 2019 to capture 2 more. So altogether, this gives us 3 different epochs over which to look for potential variability. The idea being that by comparing the 3 phase curves from these 3 observations and looking for any potential variability in their shapes, amplitudes, offsets, what have you, we can get an idea of the degree of weather that's happening in these atmospheres. One great thing about these 3 observations is that, one, they really probe two different timescales over which we get a variability. We have this multi-year timescale between 2014 and 2019, and then between the two 2019 observations, we probe this roughly 2-week timescale. And another virtue of having these three observations is that it's much easier to use these to identify and rule out any weird artifacts that we can get in our results, particularly any model-dependent findings. So this third observation acts like a tiebreaker, really. We reduced the data from each visit in the same way, and I'll quickly walk through the various things that went into actually extracting the phase curves from these observations. First off, Spitzer IRAC data has a few notable sources of systematic error that plague the data. There's a drift in the registered flux you get over the course of your observing visit. Then, even when you're pointing at the same star, the apparent size of that star on your image will fluctuate slightly in time. And that leads to very small variations in the flux you get on that image. And then finally, the perhaps most notorious systematic involved with Spitzer data is that there are subpixel sensitivity variations on the detector. These first two effects are relatively minor, and we tackled them both in a fairly similar way, just fitting a linear relationship to this trend in order to just divide it out. Dealing with these subpixel sensitivity variations, however, is a much more complicated problem. Spitzer's pointing was good enough to keep you keep your star in the same pixel generally throughout the entire observation. But these variations were happening on a much smaller scale. So even if your star was staying on the same pixel, as the star moved around on that single pixel, you get pretty significant variations in flux because of these subpixel variations. So it really came down to a bit of a lucky draw of whether or not you got placed on a particularly stable part of the detector or not. So we accounted for this just by, as we were fitting everything else, modeling or trying to map out these sensitivity variations so that when producing our final light curve, we could just normalize it all out as if this were like a flat field image. Then once these systematic effects are removed, we get on to fitting the actual astrophysical signal, which is just the combined signal of the star's emission and the planet's emission. We treat the star signal just using a transit model, assuming that the star's emission is not intrinsically changing in time. So this is just a flat line when the planet's not in transit. This y-axis here being just the flux relative to the median out of transit flux. And this big dip is the transit. Then our model of the planet signal is twofold. We have a phase curve model, which is constructed just from the sum of two harmonic sine terms, leaving their amplitudes and their offsets as free parameters in our fit. And then multiplied into this is what I call a geometric eclipse model, which is just a way of keeping track of how much of the planet can we see at a given time. So this is similar to the transit model. It's equal to 1 when the planet is anywhere but in eclipse. And when it goes behind the star in eclipse and we can't see it anymore, it just drops to 0. So we add these contributions together and we get our full light curve. This figure at the bottom here shows the fitted light curve from the first of our 2019 observations, along with its detrended data binned down into 10-minute intervals. And there's a few things we can learn just from looking at a single phase curve. So I take a quick hydration break. First off, the phase curve is fairly symmetric. As I just mentioned, the phase curve model is constructed from the sum of two harmonic sine terms. And what we found is that the first harmonic term almost exclusively dominated the fit. So this phase curve could really be well represented just by a single sine term, without any weird asymmetric bumps that you get from a second harmonic. Also, the peaks of this phase curve occur pretty close to the time of the secondary eclipse, but in fact, they occur just before that secondary eclipse. And this is a sign that the hottest part of WASP-43b's atmosphere is just past the substellar point, which is the point directly underneath the star in the direction of rotation. And this offset between those 2 points are a direct result of having strong winds in the atmosphere that blow in the direction of rotation, which is something that's been observed in many other hot Jupiters as well. And then also the minimum of the phase curve doesn't quite reach down to a level of 1, which is equivalent to having 0 emission, but does get pretty close especially within the uncertainty of our data. And this tells us that the night side is in fact very dim, and really strengthens the idea of having thick clouds on that night side. So we end up having 3 full orbit observations from which we can measure out 3 of these phase curves. And we reach the question of how do we actually fit them together, and how do we compare them in a way that allows us to really identify whether or not it's significantly changing in time. And in fact, the most obvious way to go about this may be just fit them all individually. And we did that. We gave each observation its own set of planetary parameters, like the radius, its own set of orbital parameters, like the semi-major axis, its own bliss map, which was just that way of fitting these pixel sensitivity variations, and its own phase curve parameters. And then we fit each observation separately. So if we do end up seeing very large differences in the resulting shapes, amplitudes of these light curves, then it's pretty obvious they're varying. And really, this way of fitting them captures the maximum possible case of variability between observations, because since we're keeping everything separate, we're allowing the freedom for everything to be changing between observations. So really with this in mind, we can imagine some spectrum of variability that we can explore by adjusting which fitting parameters we share between our observations when fitting them. For example, we don't really expect things like the radius of the planet, its semi-major axis, or its inclination to be changing between our observations. So our next fitting scenario shares these between the data sets, but keeps only the phase curve parameters separate. So by doing so, we only let variation come through by changes in the phase curve. And if nothing is varying at all, however, then these 3 data sets should all be best fit just by the same set of parameters for the planetary parameters, the orbital parameters, as well as the phase curve. So we went and fit our 3 observations using each of these 3 fitting scenarios and compared them. Again, the idea being that if there is some variation in the phase curve between visits, we would expect one of the 2 on the left to be preferred. But if there's no variability at all, we'd expect the one on the right to be preferred. This figure here shows the light curves from each of those fitting scenarios. Here, each row gives the light curve from each of our 3 observations, and each column shows that for each fitting scenario. We compare the goodness of fit of these by computing the Bayesian information criterion. And what we found is that the fully shared fit was strongly preferred. Here, the best fit is indicated by having the highest absolute big value, which by and far was the fully shared fit, where these other numbers just show the difference between their BIC and the preferred BIC, and we see that they're much better. That fully shared fit being the preferred scenario means that there's no major variability between the phase curves between our observations. And this figure here just sort of highlights that by showing just the fitted phase curve components. These are from our 3 individual fits of those 3 observations, where the more solid lines represent the best fit values, and the more transparent lines just give a visual of the 1 sigma uncertainties on each curve. And from this, we can see that each of these three curves, especially within their uncertainties, match up pretty well. And then I'll just add onto this figure this bright yellow curve, which is the phase curve from our fully shared fit case. And we can see that our three observations really are best fit just using this single phase curve. So what does this mean? We don't expect that the atmosphere is standing still. It's changing in some ways, but we can ask what is staying constant enough that it leads to this observational result. So we can ask what's not changing in the atmosphere. And in this picture of a cloud-driven, cloudy dynamic atmosphere, there are two main things that could be driving variations. We could have variations in the spatial distribution of our clouds, or we could have variations in the thickness of our clouds, which is closely related to their covering fraction. So to dive into this question and better interpret our observations, we turned to a modeling approach. My collaborator, Mike Roman at Leicester University, ran a suite of models, which I'll briefly describe here, but I direct you to his most recent paper if you're interested in the fine details of how these work. These models use a moderate resolution, splitting the globe up into a grid with 48 squares north to south and 96 grid points east to west. And in the vertical direction, it splits the atmosphere into 50 layers, beginning at a base pressure of about 100 bars and a top pressure of about 10 to the minus 5 bars. But the most important part of this model is how it treats its clouds. First, we include clouds actively, which means that clouds are included throughout the entire duration of the model, rather than being post-processed in at the end. And this accounts for how cloud opacity, scattering could induce feedback on the cloud, on the planet's temperature structure. And then we tested different possible cloud thicknesses. In reality, the cloud thickness depends on this complicated balance between when the gas's temperature rises above the particular cloud molecule's condensation temperature. You'll have this vertical mixing that brings cloud particles upward in the atmosphere, and gravitational settling that will bring them down through the atmosphere. But capturing all these fine effects are pretty computationally expensive, and their relative degrees of strength aren't very well constrained. So we instead adopted a more straightforward approach where we allowed our clouds to form and just defined the maximum vertical extent to which they were allowed to go before we truncated them. And we parameterized this thickness just in terms of the layers of the atmosphere, letting our clouds extend in 5-layer intervals, where each 5 layers roughly is roughly equivalent to about 1 pressure scale height through the atmosphere. So our cloud thickness was allowed to vary roughly between 1 to 9 pressure scale heights. And then finally, we tested 2 potential sets of cloud species. The details here aren't very important, but the full set of species, which I refer to here as all clouds, includes 13 species of silicates, oxides, and metals, where some recent works have found that some of these species, particularly iron and nickel, have very low nucleation rates. And so we also tested a nucleation limited case where we just removed these species from the model. And also a hallmark of this model is how it probes the time domain, tracking the atmosphere as it actively evolves. The initial state of the model was a cloud-free homogeneous atmosphere that we let loose to run for about 3,500 rotations of the planet. And all throughout that run, the temperature structure was allowed to change. We allowed clouds to form and evolve and induce their own feedback. And then near the end of the simulation, we started taking outputs at 100-day intervals, which allowed us to probe any time variability in the atmosphere that may be due to this active weather. And from these outputs, we backed out what the phase curve would look like in the Spitzer 4.5 micron bandpass. Our main idea here is that by running these models, and particularly by running a model with a particular cloud thickness forward in time, we can test whether or not we see any differences because the spatial distribution of those clouds is changing in time. And then also by comparing these models to our observational results, we can see what cloud thicknesses are consistent with the data and if that may be in fact changing in time. And these are our results. These two plots show the model phase curves taken from one output time, where each color represents a different cloud thickness. The top panel shows the results for this all clouds composition case, and the bottom panel is our nucleation limited case. And there's a few results to unpack here, but mainly what we found is that when running these models forward in time, these phase curves did not change significantly. They remained pretty constant in time. Now, this doesn't quite rule out the idea that the spatial distribution of these clouds might be changing, but just goes to show that our phase curves aren't sensitive to any changes in the spatial distribution of these clouds if it is indeed changing. And also comparing the top and the bottom panels here, there are some slight differences in the phase curves for a given thickness. But largely, we found that when you change the composition case, this choice didn't make a huge difference in our results, which will become more clear on the next slide. So, but with these in mind, or with these in hand, we can move on to comparing them to our observations to try to constrain the cloud thickness and see if that may or may not be changing in time. We used a chi-square comparison between our observed data and these model phase curves to try to constrain the possible cloud thickness. And what we found is that the data is really only consistent with a fairly limited range of cloud thicknesses. This plot here shows the results of this chi-square comparison on this fully shared set of data, which are the three observations combined into one, where I just converted this chi-square value into a sigma value on the y-axis here, and show this as a function of the cloud layer. Here, higher sigma just means that we can rule out that model at a higher significance level. In the case of our all clouds composition, the data is only consistent with roughly 20 to 25 cloud layers. And when we go to the nucleation limited case, that range gets a little higher, and it's roughly consistent with only 20 to 30 layers. And that's what I meant by saying that the results didn't change terribly much when we changed between our composition cases. So on WASP-43b, we find that the cloud thickness is likely within this 20 to 30 layer range, which in physical terms means the cloud thickness roughly spans 4 to 6 pressure scale heights. Also, we found that we get the same result whether or not we analyze all three sets of data together, or if we take each one individually. Even when we ran this comparison on just the individual phase curves separately, we found that each phase curve was consistent with the exact same range of cloud thickness. And what this tells us is that the cloud thickness is staying within this 4 to 6 pressure scale height range between our three observations. And if it is changing at all, it's not by more than 2 pressure scale heights. It's staying within this range. So what do we learn from this? For one, we learned that hot Jupiters are nothing like Mars. Because if you recall back to the story at the beginning, Mars experiences these periods of total clarity where there's almost no clouds, and these periods of total obscurity dominated by these thick global dust storms, where this radical change in cloud thickness is not at all something we're seeing on WASP-43b. The idea being that the total cloud coverage is remaining fairly constant. And this is very important because it shows that even if you observe a single phase curve of a planet, you're still getting a good idea of the nature of that atmosphere. without having to worry that the picture you're seeing isn't going to be changing dramatically between observations. So all these single epoch Spitzer phase curves that have been measured are pretty trustworthy. It's not the case that these phase curves just captured some single snapshot of the system that's changing dramatically in time and would have changed wildly since the last time you observed it. Instead, we can trust that these single observations are capturing a good picture of the equilibrium state of the atmosphere. And then I'll just leave up this slide of summary, and we can open up to questions.
Thank you for your talk. Are there any questions from the audience? I can see there's a question from Kevin.
Hey, this is Kevin Stevenson. Great talk. I really enjoyed it. I have a couple of questions, but I'll start with one sort of physical interpretation question. The variations that you saw in the phase curve, you asked the question, is this due to planet variability? But the other question that that I didn't hear asked is this due to stellar variability? And we know that the stars rotating, spots are coming in and out of view, and even on the archive this morning, there was a paper that said the stellar rotation was about 7.5 days. So, is it possible that some of the variability that we're seeing between these different phase curves is due to spots from the star rather than essential physical variability from the planet?
It's certainly possible that such stellar variability could be causing minor variations that we see in these phase curves, especially within these fairly wide uncertainties that we see on this curve. But really, one other reason why WASP-43b was a great target for this study that I didn't really get into is that we are pretty confident that the host star WASP-43b isn't all very active. WASP-43b has been observed pretty extensively in the optical, and we have seen almost no variations in any of these optical measurements. And since stellar variability is really more prominent in the optical, and we aren't seeing this, we can be pretty confident that any stellar variability isn't coming through in these Spitzer phase curves.
It might be worth testing whether you can achieve a good fit with a quadratic model that's different between each of the visits, but then assuming the same Spitzer planet parameters, just to see if you get a good fit. I think that would prove or disprove that statement that you just made. And my second question is relating to the 2014 observation. Aaron May did a follow-up fit that achieved what I think would be more comparable to the purple and blue fits, at least in terms of the night side flux coming in around 1,000 ppm. I'm just curious if you looked at that fit to the 2014 data, compared it to what you achieved for the 2019.
Yep, and you're pretty much exactly right that her fit, which went into a much deeper dive into trying to treat these various systematics, it did match up extremely well with, let me flip to a more clear, it did match up very well with these purple and blue curves, which are our 2019 observations. And so even though in our analysis, we see that this 2014 curve, its minimum amplitude goes a little bit lower. It has a fairly high uncertainty at this minimum level. We're still pretty confident that it is in fact consistent with these other curves, especially because that's what Aaron May found as well.
Okay, great, thank you, and nice work.
Thank you. Thank you.
Are there more questions in the audience? Yes.
Yeah. So this is cool and comforting that we can trust Spitzer phase curves, I guess. But I was wondering if the level of variability you see in these models would be detectable with JWST.
Certainly. Well, I can't say for certain, but it's definitely possible. And in fact, that's something we're starting to look into. Say, if we think that at least the cloud thicknesses are staying within some certain range, given our Spitzer uncertainties, we're currently looking into whether or not we could like narrow down this range given the uncertainties we expect with NIRI or NIRCam. So possibly, but we'll see.
Cool, thanks.
So as a non-exoplanet scientist, I don't really know what the difference or like how clouds are being defined for like when you were showing the plots at the beginning that were like the cloud to gas ratio, how do you define clouds versus just the gas in the atmosphere? Like, is it all the same, or does it have to do with the opacity of the, I don't know, composite atmosphere? Like, what does it all mean, I guess?
They're mainly treated as separate sources of opacity. Clouds form by gaseous molecules condensing out of that gas, given like based on both the like phase structure of that molecule and the thermal structure of that atmosphere. And so that's essentially modeled just by tracking that thermal structure of the atmosphere. And for the given set of species that you're considering, which are the different molecules that we think the clouds might be made of, we take, like, say, one species condenses at a particular temperature and the gas drops below that temperature. We model the cloud as forming in that temperature regime. And often from what I understand, the mass of a cloud particle in these models is really also tied into like the difference between the local gas temperature and that condensation temperature, and like how much of that cloud we might expect to be forming given the local temperature. But really, they're just separate sources of opacity scattering from the gas.
Okay.
I have last one question. So do we know anything about the magnetic field of the planet? Whether even though the stellar activity level is pretty low, if it's interacting with the planet's magnetic field and that may cause any certain changes in phase?
Maybe. I know that this question of like magnetic fields has been looked into in this variability context for at least one other planet. I think Koro 2b. I'm not familiar if that's been addressed or even measured at all for WASP-43b or not. But I'd have to look that up.
I think we have a question from Everett.
Yeah, really excellent talk and thorough work. I was wondering with those three phase curves, just looking by eye, it looks like they may be at the 2 sigma level. And I know many claims in astronomy have been made that these would look different. And so I was just wondering what kind of confidence level or sigma difference they are from, let's say, green from the mean.
Right. Well, these transparent lines roughly trace the 1 sigma level of uncertainty. Might miss it just a little bit. But when you consider it all taken together, especially at the minimum here, the difference is roughly at the 1 sigma level. And especially as I touched on before, other analyses of what's this green curve have brought that minimum up closer to these purple and blue curves, and especially the yellow one. We could very confidently say that they're consistent with one another.
Okay, thank you.
Yeah, thank you.
Okay. If there are no more questions, let's
Thanks
again.
You can turn on your video. So I will stop recording